There we go. So this is lecture 15, and today is the 5th of May. Okay. So let's quickly glance through what we've so far covered. We are still covering the force harmonic excitation of damped systems. So let's summarize where we are. We looked at the response of a, a damped system under the action of a harmonic load, a special kind of harmonic load that we also studied was rotating unbalance. Okay. And we also looked at the special case of time dependent input displacement. That is, when instead of having a forcing function, we have a that is acting on the mass, the base of the structure is subjected to some time dependent input displacement. And we only considered, of course, the case that that input displacement is of harmonic nature. Now, the question that I'm sure at least some of you will ask is, I mean, what's the whole purpose, objective of studying the uh, vibratory impact of a force or a displacement on a system? The ultimate goal, one of the goals, obviously, for studying this topic is that how do we prevent any kind of adverse impact on the system when it is subjected to a motion? Or how do we isolate the effect of these forces or the displacement on the structure? So that brings us to a topic called vibration isolation. Okay. So what is vibration isolation? In at least studying harmonic excitation, we have realized that there are two sources of disturbance to a system. Either a force causes the disturbance or a motion meaning some kind of a displacement. So we're going to look at what is the meaning, or what is how we can what strategize an approach, or what is a strategy to isolate either the effect of the force or isolate the effect of motion. Okay, how do we do that? For instance, if you have a chiller on roof of a structure, this chiller is generating a harmonic load, especially if it is rotating unbalance. It causes a a harmonic force, but we don't want the structure shake due to the action of this operating system of a force, right? Or if you want to isolate, for instance, the effect of, for instance, earthquake at the base of a structure, how do we minimize that effect? Or let's say you have a car driving over a rough road. How do we minimize the effect of that road roughness, which causes a motion in the system? Or you have a rotating machinery with a heavy mass rotating. The shaft is supported by some kind of bearings. How do we minimize the potential damage due to this rotation to this bearing system, or how do you design the bearing system to be able to withstand the effect of the rotation of this heavy mass? So that's the meaning of vibration isolation. So we need to define a criteria for what we mean by vibration isolation. So look at both cases. Let's say if you have a force acting on a system, which of course the only force we have so far covered is a harmonic load. Okay. So this system moves, and as a result of this motion, which is caused due to this force, this support system, which is a mass and a spring, experience a force that is generated to do this external force. But what is that force? If you look at the free body diagram, what are that force? What is that force? Is F of K and F of C. So the force that is transmitted as a result of this applied load to the foundation is this total force of these two, you know, support component. Same thing when you have a system that is experiencing a motion due to an unexpected or applied displacement or the motion at the base of the structure. If you go through and try to find out what that force transmitted is, you'll be, I'm sure you can easily see that the force comes down to the force that is carried by these two. So in order to develop a strategy for vibration isolation, we introduce or define a quantity called transmissibility transmissibility ratio. This transmissibility ratio is defined this way. For the case of forced vibration, that is the force we want to isolate the effect of the motion caused due to that force, this transmissibility ratio is what? We want to reduce the effect of maximum force transmitted, okay, over the maximum applied force. So the goal is that we want to keep this minimum as low as possible. Or in other words, we want to make sure that the maximum force that is transmitted to the base foundation compared with maximum force that is applied is very, very little. So the foundation or the support structure is not damaged. If this is a rotating machinery, okay, this is the rotating disc, we want to make sure that these bearings, although this heavy mass is rotating, we want to make sure the force that is transmitted to this support is much less than the force caused due to this rotation. If the system is subjected to a displacement, we want to reduce the effect of that maximum displacement of the mass, okay, over the maximum applied displacement. So again, here we want to make sure that although this may be a very large displacement, Okay, when this mass moves, that displacement compared with this is very, very little. Now, by defining these quantities, let's see how we can actually come up with a strategy or come up with a mathematical formulation that helps us to perform this action or achieve this objective of reducing the effect of the force or the effect of motion. Okay, so let's focus on the force isolation first, meaning that we want to find the transmissibility ratio in this case. Okay, in this case, if you have a harmonic load, right, which is all we have seen so far, this is the input force, right? And what is the force that is transmitted? Is what? Is Ku plus Cu dot. But what is U and what is U dot? U is a displacement and velocity caused due to this motion, right? So we remember that U is what? U is F naught over K times H times sine of omega t minus theta, right? If you have a harmonic force acting on a system, this is U. And what is U dot? U dot would be just derivative of that. So it would be F naught over K H omega cosine of omega t minus theta. So we know what the maximum force applied is. This is the maximum applied force, right? The amplitude of this harmonic force. But what is the maximum value of this? First of all, this force is what? K times U, this is U. So K times F naught over K, H sine omega t minus theta, okay, plus C times this, F naught over K, H omega cosine omega t minus theta. So this and that cancel out. So let me sort of rearrange this. The transmitted force then becomes F0, okay, H times sine omega t minus theta plus F0H, okay, but I would just rearrange these, times C omega over K, okay, times cosine omega t minus theta. But how do I find the maximum value of this? Look here. You have, look at these two quantities. Let me, if I call this alpha, this is beta. So you have, again, alpha times the sine of a function, beta times cosine of a function, right? You remember you had A sine D plus B cosine D. I can always write this as A squared plus B squared, right? Over A square root of this sine D plus B over this cosine D. And this always can be converted to sine of the sum of two angles. This is an angle. This is sine of an angle. This is cosine of an angle. Because we've done this before. Sum of the square of these is always one. So that means this is a sine of an angle gamma. This is a cosine of an angle gamma. So trig identity tells me that this is a sinusoidal function, right? Okay, so sine of gamma minus d. But I don't care about this part. What I'm concluding is that this is this amplitude times the sine function. So this amplitude, which in this case is that alpha squared plus beta squared, is that maximum value that we were talking about, right? So this maximum value would be simply what? Would be this F0 H squared plus F0 H squared times what? Um, C squared omega squared over K squared, right? So let me simplify this. F0H factored out comes out of this radical, so I have F0H times 1 plus C squared omega squared over K squared, okay? Now, I don't like this. First, let me look at how I can replace this with another sort of a expression. I will write C squared omega squared over K squared, multiply this by omega n squared, divided by omega n squared, and then I would separate these. So this would end up being C squared, okay, omega n squared over K squared times omega over omega n squared is R squared. But let's look at this. I can replace omega n squared. Omega n squared is what? Is K over M. So if I substitute that here, I have K, let me write this, I have C squared K over K squared M. This and this cancel out. So this becomes C squared over Km. But you remember that critical damping was what? 2 square root of Km. Remember that? Right? So what I have here, I have what? I have, I'm going to multiply this by 4, divided by, if I multiply this by 4, divided by 4, I have 4 C squared over 4 Km. So in other words, I have C critical squared. Or ratio of C over C critical is what? Damping ratio, right? So this is then 4 zeta squared. Here we go. So I converted this to this nice term. So therefore, that maximum force transmitted becomes what? F0 times H, which is what? H was 1 minus R squared plus 4 zeta squared R squared times 1 plus what? 1 plus 4 zeta squared R squared. So this is not that clean. So let me go to the next page and rewrite that again. So from these derivations, you can see that then the maximum force transmitted becomes, okay, uh, F naught times 1 plus 4 zeta squared r squared divided by 1 minus r squared plus 4 zeta squared r squared. So what was the maximum force input max? Was F naught, right? So if you divide that to this transmissibility ratio, which was defined as the maximum force transmitted to the maximum applied force, becomes simply, I would just put them in the same um, radical. So that's what it comes out to be. This is the result. So this is very interesting. So we could prove that if you have a forcing function of harmonic nature, obviously, acting on a system, in order to reduce the effect of the applied load, we need to minimize this value or keep this value as small as possible compared to the applied force. Okay? Ironically, very interesting that if you even consider the case of input displacement, that is, you have a system subjected to this. You remember the formulation we did, okay? And that's what it was, okay? You can see that even if you have an input displacement, and as long as the input displacement is of harmonic shape, so you find y max, okay, which is y, you find the maximum displacement, which is u max from here, which you know what that is, f0 times h times, that would be basically you by um, max, you end up with the same transmissibility function expression. I don't go through the mathematics of that as unnecessary. We're not in the business of uh, going through these derivations to prove a mathematical term because we are interested in the end results. Our goal is to be able to understand this and interpret that. So, what is the meaning of this expression? In order to fully understand what this transmissibility ratio means, let's plot that function. If you plot this function, you can see that at r equal to 0, right? This cancels out, this cancels out, and this cancels out. So this is 1. So all of these curves start at r equal to 0 at value of 1. So we are plotting transmissibility ratio versus frequency ratio. Now, if zeta is 0, if zeta is 0, what happens? Transmissibility ratio becomes 1 over 1 minus this. Does this look familiar? Yes, it does. This was the frequency response function for an undamped system subjected to harmonic load. So we know that at R increases, this goes to infinity, okay? And as further increases, you make an observation that at r equal to square root of 2 comes to become 1 and then goes to 0, okay? Now, as you plot this function, you will see something interesting. All these curves look like this. They all go through the same r is equal to square root of 2, no matter what the value of zeta is. You can easily see that by putting r is equal to the square root of 2, which means this would be 1, okay? So you have 1 plus um, this and 1 plus that, right? So that means transmissibility ratio is 1. So at r equal to square root of 2, all of them hit this line, no matter what the value is. And the only thing is, okay, let's say this was zeta 0.1, this zeta 0.3, let's say this is zeta 0.5. The only thing is that, so in other words, this is zeta 0.5, this is zeta 0.3, this is zeta 0.1. And of course, if zeta increases further, you'll see that these all fall below this line. But let's focus on this plot. The goal is for vibrational isolation, as I said, we want to keep transmissibility ratio to be less than 1 because we want to make sure that the force transmitted to the system is less than the force, maximum force, value of the force applied, and be as little as possible. Same thing, displacement transmitted is less than the displacement experienced by the system. So in other words, we are interested what is happening below this line. What does that mean? First of all, look at it here. We can make several observations. Observation number one is this, that if r is less than square root of 2, okay? If r is less than square root of 2, and you have an damped system, as long as, of course, the damping is less than 0.7, transmissibility ratio is always greater than 1, right? So that's not good. So we're interested only when r is greater than the square root of 2, when transmissibility ratio is less than 1. That is, this is the desirable range. That means if you have a control over the frequency of the forcing function, a source of excitation, and the natural frequency of the system is fixed. In other words, you have an existing system subjected to a harmonic excitation. You've got to make sure that the operating frequency is always greater than square root of 2 of natural frequency of the system, so that you reduce the effect of that applied load. Even within this range, as you can see, the lower the value of damping is, right, the better the effect, the lower the value of transmissibility ratio would be. Okay? So in other words, if you have a system, forced um, vibration, and the system is undamped, okay, the transmissibility ratio would be less than the case when the system is damped. Okay. Usually, of course, okay, and of course, um, if you have a system that is existing, right? Let's say you have a rotating machinery and you want to design the support structure so that it can better withstand the effect of, say, rotating unbalance, okay? You can use this criteria to design that foundation. So I'm going to do, in fact, an example just like that so that you can see this, okay? But before doing that, let me elaborate a little bit more what I said, okay? I said that you want that this be greater than 2, right? Or omega over omega n is greater than 2, a square root of 2, or omega n is less than 1 over the square root 2 of omega. If you have a system that you have no control over this, if you have control over this, so you would increase it as much as possible, so you would be here, right? You would be somewhere here. But if you don't have control over the forcing function, you have a system, you want to put, let's say, you want to design a supported structure to support a rotating piece of machinery. Okay. That means you need to design that system such that its natural frequency is less than this. Okay. Or in other words, you need to reduce this as much as possible. Reducing this as much as possible, that means you're reducing it. You usually don't have much control over the mass, right? So that means you need to reduce K. So the best isolation system, the best supported structure that can reduce the impact of the applied load is a stiffness that is very, very low. That is a support that is very, very soft. In other words, chewing gum is better than rubber because it's very soft. However, the problem is that under the action of just the static load being the weight of the structure, chewing gum just goes through huge deformation, and you don't want that. Obviously, think of it this way, okay? That, for instance, you have a rotating machinery. You want to design a bearing to support the rotating impact of this system. You say, wow, the best thing is to do is uh, have bearings that are made of cotton. Of course, they would isolate the vibration really great, but the whole system would collapse under its own weight. So it's a balancing act that you don't want a stiffness that is too soft, but it is, too soft, meaning that not so soft that the static displacement is large, okay? And that, but yet as soft as possible. So with all that said, let me stop here and do an example problem of 2 to show you the application. Any questions though, before I start? So let me, you know, first go with a simple problem. Let's say you have a rotating machinery. Basically, you have a um, this disc that weighs 2,200 pounds, and this disc is a rotating machinery, so you have a rotating unbalance at a position of E, that is the distance of the unbalanced mass from the center of rotation, being roughly 1 inch. And the mass of this rotating unbalance is 1.3 ounce. Okay. The machine, okay, operates at 7,200 RPM. Okay. But we
What does it
want
say right below the like rotating disc? Is that 0 H0?
this one. This one here.
That one and the one below it.
This one is E, which is the
Okay.
distance from the center of rotation to the mass, unbalanced mass. Okay. And this is
Yeah.
M sub E, which is 1.3 ounce. Okay. So what we want to design, okay, an isolation system. Okay. So they force transmitted, okay, to the foundation is less than 50 pounds. So in other words, this is the problem you have. This is that mass with that rotating unbalance, right? Okay. It is supported by this beam, of course, here. Okay. And you want to make sure that the force that is transmitted, this force here, F of K plus F of C, is less than 50 pounds, despite the fact that this machinery is 2,200 pounds and operating at this frequency. How in the world we can make this happen? First, to simplify the problem, I'm assuming a damping ratio is 0 for this particular problem. Okay, so make the problem a little bit easier. So transmissibility ratio then reduces to this. Okay, so, but what is the applied force? But this is what? Transmissibility ratio is the maximum force transmitted to the maximum force input. So, what is the input force max? We remember from discussion on rotating unbalance that the amplitude of that uh, forcing function is this. So this is the maximum force input or applied to the system. So let's evaluate that. That would be 1.33, it is ounce. Need to divide that. This is actually the weight, not mass. So divided by G, and we need to divide it by 16 because it's ounce divided by, make it pound, okay, times 1 inch, which is 1/12 of a foot, times omega squared. Omega squared, omega is given as 7,200 RPM, so times 2 pi over 60 would be 754 radians per second. So 754 squared. So the maximum input force is going to be 122.7. That's what the result of this operation is. Okay. So what did we say that we want this, which is going to be uh, the ratio of the maximum force transmitted. Maximum force transmitted, we want that to be 50 pounds, no more than that, over the maximum input force is this, right? So from here, we can find what should be R, 1.86, where R is omega over omega n, 1.86. We have omega here, 754. So we can find omega n. Omega n comes out to be 405 radians per second. So we need to design this system such that the natural frequency of this system is this, okay? But what does that mean? We know that what this tells us, K is what? M times omega n squared. Because we want to design this as stiffness, right? We have no control over the mass. Mass is given. So we only have control over K. K is M times omega n squared. So that is 2,200 pound force over 386 times 405 squared. That gives us a K of 9.4 times 10 to the 5 pound per inch. So if we design that support structure to have a stiffness of this much, that would guarantee that the force transmitted will be only 50 pounds. But is this safe enough? In other words, is this not too soft to cause too much static displacement under its own weight? So let's find that out. The static displacement under that weight, okay, is W divided weight divided by the stiffness, 9.4 times 10 to the 5, which give me a static displacement of roughly 2.3 times 10 to the negative 3 inches, which is almost zero. So this is a good stiffness value to use to keep this uh, effect of the force transmitted to less than 50 pounds. Okay, any questions? Any question on this?
Yeah, what is that 386 you divided by?
Oh, you see, that's 32.2 times 12. You see that converting this to, this is uh, pound force divided by pound to make it pound mass.
Okay.
So that's G times, G is 32.2 meters, foot per second squared. So I need to also divide it by 12 to convert it to inch. So that's a conversion factor to convert pound force to pound mass. So let me
Professor,
do, yes.
in regards to that, when we're giving like a mass in terms of pounds, should we just assume that it's a pounds mass and always do that, or can
Well,
we assume that it's pounds
yeah, if
force?
it is a pound mass, no, we don't do that. If it is pound force, you convert it to pound mass because omega n is K over M and M is pound mass. In, of course, the good units, SI units, that's kilogram. So it's easy. But unfortunately, we have this pound force and pound mass, and we got to make sure that everything is kept in pound mass. In this problem, the weight was given as 2,200 pound. It says the weight of the disk is, and the weight, I shouldn't have put M sub E, the weight of that unbalance is 1.3 ounce. Does it answer your question?
Yeah, it does. Thank you.
Good, thank you. All right, so let me do, I think I can do another problem. We have 3 minutes left. Why not do another problem? And this would be actually a more interesting problem. At least that's what I think. So let's say this time I consider that same machinery, okay, but or similar kind of a problem. You have a massless, again, beam supporting a weight of 3,860 pound force, okay, supported by these bearings. The beam has these geometric and material properties, okay, I of 120 inch to the 4. So this is a machinery. Inside the machine, okay, a piston moves up and down, okay, and generates a force of magnitude 7,000 pounds. In other words, this up and down piston is generating supposedly a harmonic load. So this F of t is F naught sine omega t. This maximum force that is generated is 7,000 pounds. So I should have said generate a maximum force of 7,000 pounds. Okay. Omega, which is the frequency of this motion, is 60 radians per second. Okay. And the damping ratio of the system is 10%. Okay. We want to find A, the amplitude of the motion of this machine. Okay. And then find the force transmitted, okay, to the foundation, to the beam. So that's what the problem is asking us. In other words, you have a system like this. This is the mass. It is subjected to a force F0 sine omega t. This is the support, which is that beam. Okay. This is C, this is K. Okay. Where beam is a simply supported beam with a load in the middle. So K is 48 EI over L cubed. Okay. So if you substitute for those values, you see this comes out to be 10 to the power of 5 pounds per inch. Okay. Natural frequency, which is K over M, would be 10 to the 5. Weight is given 3,860 divided by that conversion factor of 386. This comes out to be 100 radians per second. Okay. Okay. So the ratio, the frequency ratio, which is omega over omega n, is 60 over 100, because this was given. So is 0.6. So what is the Umax? Part A. Maximum displacement that obviously this system is going to experience is this times h, which is f0 over k 1 minus r squared plus 4 zeta squared r squared. F naught is given, is 7,000 pounds. K, we found it. R is 0.6. Zeta is given as 10%. So if you substitute for these, since we're running out of time, I would just do it quickly. Sorry about that. So we will have basically 7,000 divided by 10 to the 5 divided by 1 minus 0.6 squared, okay, squared plus 4, zeta was 0.1 times 0.6 squared. If you evaluate this, this comes out to be roughly 0.11 inches Umax. So that's the maximum displacement this machine is going to experience. But now we want to know how much is the force that is transmitted by this system. So the force transmitted, okay, is what? Okay, transmissibility ratio is what? Remember, we want to find the problem is asking force transmitted to the foundation, right? So maximum force. Transmissibility ratio is this 1 plus 4 zeta squared r squared over 1 minus r squared plus 4 zeta squared r squared. This is the maximum force transmitted, okay, over the maximum force input to the system, which is 7,000. So we have R, we have zeta, and so on. You can find the force transmitted due to this, and I will give you the value. I think I have it here, which is going to be, let me see. Okay. Here we go. It's going to be 10,827 pounds. So due to the action of this rotating machinery with that frequency and the force of 7,000 pounds, you're actually transmitting a force which is much larger than the maximum applied force. So what do you need to do? Increase the stiffness of this system to reduce that force. Okay, so I'm going to stop here and see you either during my office hours, which I just sent you an email, start at 10 past 11 today, and or I will see you on Friday. Thank you for your listening, and hopefully see you soon.